Okay, hello everyone. Now let's wrap up this lecture talking about some aspects of the kinetic molecular theory. All right, so most collisions are inelastic, right? So like you drop a ball on the floor, eventually it will stop bouncing because you're going to lose some of that energy to sound energy, to heat, and also to other forms of energy. So most collisions are inelastic. I can't really think of a situation where it'll be elastic, but most of them are inelastic collisions. Okay, so let's go over this checkpoint here. All right, so the kinetic molecular theory assumes the temperature of a gas on the macroscopic scale is directly proportional to the average kinetic energy of the particles on the atomic scale. Use this assumption to explain what would happen to particles of a gas when the temperature of a gas increases. Okay, so what happens to the average kinetic energy of the gas particles? All right. Okay. Okay. So when the temperature of a gas increases, right, we have more energy. So when we have more energy, the speed of the particles will increase. So in this case, when the temperature increases, okay, the speed of the gas particles increase. Okay, and this will cause the kinetic energy of the particles to increase. Okay. That's why when we say that when we heat something up on the macroscopic scale, we're saying the particles in on the atomic scale, the particles, they're actually moving much more rapidly, and when they do that, they generate energy. They're getting energy from somewhere, and that energy is transferred to cause the particles to move, and that's when the temperature. And when they do move, they're going to collide and transfer energy, and that transfer energy is what drives the temperature up. So as you raise the temperature, your average kinetic energy is going to increase, and as you take away that energy, eventually the temperature goes down. The particles don't move as fast, and then the temperature of the object will decrease because the particles are no longer moving at elevated with elevated energy. Okay, so that's pretty much how energy works. It's a very conceptual thing to think about, but energy is pretty much the transfer of heat, and that has to do with how things basically communicate energy between each other. Okay. All right. So let's talk more about the average kinetic energy of a gas. So it's only proportional to the temperature of the gas and nothing else. And we're just talking about the average kinetic energy. If we're talking about, think about two things, right? Two things can have different masses, right? But at the same temperature, they'll have the molecules, or the things that make up the object will have the same kinetic energy because they have the same let's say here, they have the same temperature. So two objects at the same temperature, they'll have the same kinetic energy. So that's what we're trying to get across. Now, will those particles have the same speed? Probably, probably not. They probably won't have the same speed. Um, but on average, they'll have the same kinetic energy because they have the same temperature. So things at the same temperature, they will have the same um, they'll have the same average kinetic energy, but that doesn't mean they'll have the same speed. Okay, so speed is a little bit different and it's influenced by different things, but for kinetic energy, it only depends on the temperature. Okay, so if we look at these, so if we think about a little more specifically here, so at a given instance, right, a few particles are moving very slowly and a few are moving very rapidly, right? But the bulk of the particles, they'll have velocities that are, and hence kinetic energies somewhere in between the two extremes. And I'll show you what I mean, okay? If we look at this curve here, so the average kinetic energy is proportional to the temperature, and so at a lower temperature, we're going to see most of the molecules are going to have kinetic energy that's in between the two, where the curve meets the axis. So only a few of them will have low kinetic energy, and only a few parts of them will have a high kinetic energy. But most of them, they'll have this, on average, most of the molecules will be in this range, right? In this range. Right here. Okay? So, but as we increase the temperature, right, now more molecules are going to have more energy, so the curve broadens out. So the lower the temperature, so this is what we call the Boltzmann distribution of kinetic energy. So at lower temperatures, your curve is going to get much more defined and much more taller. But as you go to higher temperatures, that distribution of energy is going to be felt by a lot more molecules. So it's going to flatten the curve, and your average kinetic energy for each molecule is going to pretty much all the molecules will eventually have the same average kinetic energy. So in this case, see, as it flattens down, what we're saying is that eventually you're going to have the distribution of the kinetic energies will be pretty much even as you increase the kinetic energy. So at higher temperatures, you're going to have molecules that there's going to be a higher fraction of molecules that have a higher kinetic energy, right? And we see here this curve. If we look at the curve, if we compare the curves here, you see there's a lot more percentage that have the highest kinetic energy if we compare the low end of two curves. So as you increase the temperature, you're increasing the distribution of kinetic energy. So as you increase the temperature, you're going to have a lot more molecules having low kinetic energy, high kinetic energy. So the distribution will change. So essentially what we're seeing here is as we increase the temperature, we're going to see a lot more molecules having higher kinetic energy and lower kinetic energy. So the distribution of kinetic energy will definitely increase to more molecules as you increase the temperature. So the distribution here, and then what that would mean is that the average kinetic energy is going to be more towards the center in this case. Or it's going to be more towards, it's going to be more even. So on average, so on average, in this case, on average, the kinetic energy of all the molecules will fall dead in the center as you increase the temperature. So that's how you should see it. At lower temperatures, most of the molecules will have kinetic energies between the two extremes, or between the two extremes. And as you increase in temperature, pretty much you're going to have a number of particles that will basically be evenly distributed. So in this graph here, as we increase the temperature, we're going to make the distribution wider, so that you're going to have a much more even distribution of particles, having speeds between the low end and the high end. So eventually, as we increase the temperature, the range of pretty much the kinetic energy for all the particles will increase, and it will shift the distribution to a little bit more even distribution in this case. Okay? All right. So that is kinetic energy. We can see a similar trend for velocity, and we'll talk about that when we get there. Okay? All right. So on average, there's going to be gas molecules moving slower than the others, and faster than the others. So it's more correct to say that on average, the average speed, we could calculate the average speed of gas particle, but we can't calculate every speed for every molecule. It's not very representative. So all we can do is calculate the average speed. Okay, so let's calculate the relative velocities of molecules here. Okay, so two gases at the same temperature must have the same average kinetic energy, right? Because of the equation, because of the fact that kinetic energy is only dependent on the temperature of the sample at which you're looking at, right? So we can represent this with the following equation. We know that kinetic energy equals 1/2 mass times velocity squared. So they must be equal at the same temperature, right? So we can actually simplify this equation by multiplying both sides by 2. Okay, so we multiply both sides by 2. Okay, we will cancel out this fraction here. So if we multiply by 2, we can get rid of the fraction there. And we have now but if you just divide both sides by 1/2, you get the same idea, right? So we can write this equation as mass of hydrogen times velocity of hydrogen squared equals the mass of oxygen. Oops. Times the velocity of oxygen squared. Okay? So now we can rearrange the equation so we're comparing velocities and masses to each other. So we get velocity of hydrogen squared over the velocity of oxygen squared equals the mass of oxygen over the mass of hydrogen. So you see the velocity, the ratio of velocities is inversely proportional to their masses. So if we take the square of both sides, we can see that we can now compare the velocities directly. So velocity of H2 over the velocity of O2 equals the square root of the mass of oxygen over the mass of hydrogen. Okay. So in this case, if we don't know the mass of oxygen, we can simply relate this to their molar mass, because we know mass and molar mass, they're directly proportional. So if we had some mass of oxygen, typically 5 grams of oxygen, it'll take I think, a less amount of hydrogen to get a mole, right? And then more a mass of oxygen to get a mole. So it's directly proportional here. So in this case, we could just simplify this to just the molar mass. Okay? Molar mass of O2 over the molar mass of H2. Okay? Here we go. All right, so using this relationship, we can calculate the velocity of, well, not the exact velocity, because that will depend on, it's a little bit too hard to do that. So in this case, we're going to calculate the average velocity of the H2 molecule at 0 degrees Celsius. If we know the average velocity of O2 molecule at that temperature is 425. So we can actually calculate we can actually use this equation to calculate the velocity of something we don't know using the velocity of something else. Okay? So we have velocity of hydrogen oxygen, and we know it's equal to the square root of their masses, and inversely, so the molar mass of O2 over the molar mass of H2. Okay, so if we work this equation out, we have H2 here, and we know that the velocity of oxygen is 425 meters per second here, and we can set it to the inverse of their molar masses. Oxygen is going to be 32.0 grams per mole. Then hydrogen is going to be about 2.02 grams per mole. Grams per mole will cancel out. And then we can solve here by multiplying both sides. And we get hydrogen here equals approximately 3.9801. Or you can just, so if I simplified what's on the right-hand side of the equation that I wrote previously, that'll be equal to about 3.9801. And then we multiply this by 425 meters per second. We will get 1690 meters per second. Okay, maybe let me just write out what it should be first. So let's write out, let's keep a decimal place here, 0.5 meters per second. And so, but we can round this to 3 sig figs, so 1,690 meters per second. So, does this make sense? Well, hydrogen is much less massive, so it doesn't have as much mass than oxygen. So it should move faster. And the way we set it up here, it does indicate that it moves faster. So that is in fact our correct answer. So if you have a velocity of a gas particle and its molar mass is less, that should have the higher average velocity. So gas particles, the average speed is a little bit different because it depends on the mass of the gas. And usually hydrogen has a lower mass or lesser mass, so it will move faster than something like oxygen or argon, something even more massive. Okay, so let's stop there for today. Next time we'll go over root mean square speed and talk about how that equation is derived, and it's derived from the contributions of the kinetic molecular theory and how we define how gases behave. So I'll go over that next week. So this is the end of lecture 10, and I'll see everyone next time. All right, take care.